I'll organize the talk as follows. First, I like to talk a bit about the fundamental notions of reduction, and then I will introduce our problem to then give the main results we have obtained so far, and of course, ending with some conclusions and the present work we are doing. So let's start. Everything in this talk will be from the Lagrangian point of view. So when we study a Lagrangian system, we need to start from a configuration space. In the case of mechanics, is the tangent bundle of certain smooth manifold, and in the case of field theory, is the first jet of certain smooth bundle. By the way, here everything is smooth. Every map, every bundle. Okay, once we have our configuration bundle, we need to define a Lagrangian density, or Lagrangian in the case of mechanics, which has all of the information of our system. And then we apply a variational principle, namely the principle of stationary action, to obtain the well-known Euler-Lagrange equations. Reduction appears when our system has any kind of symmetries, and it gives us a systematic way to treat that symmetries. Mathematically, symmetries are regarded as an action of a Lie group G on our configuration space. And what we do in reduction is to define the quotient of our configuration space by this group action. And it is called the reduced space. When our Lagrangian is invariant by this action, it is well defined, the reduced Lagrangian in the reduced space. And then we can then reduce the variational principle. However, one of the main problems in reduction is that the reduced space is not a tangent bundle or a first jet, as in the case of a usual theory. So the reduced variational principle in general is not the principle of stationary action. And when applied to the reduced Lagrangian, it gives the so-called reduced equations, which are not in general Euler-Lagrange equations. In order to illustrate this, I will show you a table with the main results of reduction known in the literature. First, for mechanics, we can consider the easiest case, which is the configuration space being the tangent bundle of a Lie group and being the group of symmetries the same Lie group. In this case, we obtain the Euler-Poincare equations. More generally, we can consider any tangent bundle of any smooth manifold and the group of symmetries any Lie group. This case is more complex, and we obtain the Lagrange Poincare equations. And analogous results hold for the case of field theory by substituting the manifolds by bundles. I like to note two things. The first one is the one I said in the previous slide. The reduced spaces, which are these ones, are not tangent spaces or first jet spaces in the case of field theory, but something slightly different. For example, in this case, we have the first jet of the quotient bundle, but we have also an additional term here. Or for example, here we have the bundle of connections of this principal bundle. The second thing I want to note is that to perform this reduction, we need these omegas here. We need them to study the geometry of the reduced spaces, but also to study the reduced variations and thus the reduced equations. These omegas are connections, principal connections on certain principal bundles. So principal connections are a fundamental tool to study reduction. I think I gave the main ideas of reduction, so now I'll introduce our problem. In the known cases in the literature, the group of symmetries, G, is a Lie group that does not depend on the point of the base space. The base space, in general, is the space-time of our theory. So these kind of symmetries in physics are called global symmetries. However, there are a lot of systems which has Lie groups that vary as the point of the base space varies. In this case, we have like a family of Lie groups and a family of actions on the fibers of our configuration bundles. These kind of symmetries are the counterpart of global symmetries and are called local symmetries, and are the ones in which we are interested. The main thing we can do to study them is to gather all of our Lie groups in a Lie group fiber bundle G over X, and then gather all of our actions on a fibered action. A fibered action is basically a vertical bundle morphism such that the induced morphism in the induced map on each fiber is an action on the typical sense of the word. Then this fibered action can be straightforwardly extended to the first jet. because our theories are defined on first jets, not only in the configuration space itself. And that's the question. What is the reduction method for this kind of local symmetries? To study this problem, we need to address 3 steps, as any reduction problem. The first one is to study the geometry of the quotient bundle. In this case, it's not a typical quotient, but a fibered one. It's like putting together a lot of quotients. Then we need to study the reduced variational principle. We need to see how are the variations in this reduced space. And at last, we would like to apply the reduced variational principle to an invariant Lagrangian to obtain the reduced equations, which are the main results of reduction theory. Okay, so let's see what we have done. First, we have tried to reduce by the whole group. We start from a usual field theory, and we suppose that it is invariant by the whole first jet of G. I said before that in general, when we perform the quotient of the configuration bundle by the group of symmetries, the result, the reduced space, is not a first jet. However, in this particular case, we have an uncommon situation, and we obtain again a first jet, the first jet of the quotient bundle. Therefore, our reduced Lagrangian depends only on first jets of sections on the reduced space. We have seen also that the reduced variations are again arbitrary. So again, we are applying the principle of stationary action to the reduced Lagrangian. And therefore, the reduced equations are again the Euler-Lagrange field equations for the reduced Lagrangian. This is a very uncommon situation, as I said. And the main problem with that is that almost useless, because most physical systems are not invariant by the whole first jet, but only by a subgroup. So the main problem we have been studying is not the reduction by the whole first jet, but only by a subgroup. So let's see what have been obtained in this case. A subgroup here means a Lie group subbundle, because we don't have a Lie group itself, we have a Lie group bundle. We call, but now for simplicity, I'm calling it subgroup, but we have to take in mind, be in mind that it's a subbundle. Okay, so to better describe this H, we have fixed a connection on G over X on our Lie group bundle. This allows us to identify the first jet bundle of G with this vector bundle, where this matrix G is the Lie algebra bundle associated to our Lie group bundle. And we have picked H of this particular form. It has the same expression, but we have substituted the Lie algebra bundle by a Lie algebra subbundle, H. And we have tried to perform reduction by this kind of subgroups. As I said in the slide of the table, principal connections were a fundamental tool to study reduction. In the case of reduction by the whole group, any connection was needed, but now we need a connection, but we don't have a principal bundle to pick a principal connection, because the kind of action we have now is fibered, a fibered action, and the actions on principal bundles are actions of a Lie group on the whole total space of the bundle. So we have an analogous ones to principal connections, and those are generalized principal connections on generalized principal bundles. In terms of one forms, a generalized principal connection is a one form on the total space E, taking values on this matrix G, which now it is not a Lie algebra, but a Lie algebra bundle. And we ask this one form to satisfy two conditions, as in the case of principal bundles. The first one is that the one form defines indeed a connection on our bundle. And this is mathematically said that it behaves properly when adds on infinitesimal generators. Infinitesimal generators here can be defined in the same fashion that are defined in the case of principal bundles. The second condition is equivariance, and is the one which is more interesting. In the case of principal connections, we need to define how our connection behaves when we move a vector on the tangent bundle of the total space by the action. Phi here is the fibered action. However, now we don't have only one bundle, we have another bundle which is the Lie group bundle, and we need to pick then a couple of vectors, not just one. We have seen that the proper way to define this equivariance is by this expression, which has two terms. The first one is the same one as in the case of principal bundles, but we have now an additional term related to the other bundle. We have the bundle of Lie groups. This second term depends on nu. Nu here is the connection we have fixed before on the Lie group bundle. So, as opposite to usual principal connections, generalized principal connections are always associated to a connection on the Lie group bundle. And now we have stated our problem and defined the main tool we will need to understand it. Let's see the results we have obtained. Again, we start from a usual field theory, but we suppose now it is invariant only by h, being h of this particular form I said in the previous slide. We have found that the quotient of the first jet of E by h is this one. It's the first jet of the quotient bundle, as in the case of reaction by the whole group, but it appears an additional term, as in the classical case I showed you before in the table. But this new vector bundle is slightly different, because in the classical case, it's the cotangent bundle of the base space and the tensor product with the adjoint bundle of the principal bundle. Now we have to define this thing which is called the generalized adjoint bundle, and in which we take into account also this mathfrag H here, which is the one used to define the Lie subgroup of symmetries. So we have to perform like two quotients. The first one by the action of G, but then also by the action of H, which is a Lie algebra subbundle and in particular a vector subbundle. Therefore, the reduced Lagrangian will depend on two sections, on first jets of sections on the reduced space, but also on sections on this vector bundle. And the last step is to find the reduced variations in order to obtain the equations. We got that the reduced variations has this particular form. Variations of sigma are arbitrary, but variations of the vector sections have this form, and to express it, we need the generalized principal connection omega. In this expression, B is the curvature associated to this omega, and overlying eta is a section on the generalized adjoint bundle, seen over X, no over E. And this nabla H is a linear connection on the generalized adjoint bundle, which can be straightforwardly induced from the principal connection. So we don't need to pick an additional linear connection, but we just induce it from the generalized principal connection here. Last, when we apply these variations to our reduced Lagrangian, we obtain the reduced equations for local symmetries by these particular subgroups. This is the main result I wanted to show you today. And we see that we obtain a couple of equations. The first ones are like the usual Euler-Lagrange equations for the reduced Lagrangian, lowercase l, but with an additional term related to the curvature. And the second one is like the Euler-Poincare equation and can be regarded as a conservation law using the Noether theorem. So formally, they are pretty similar to the ones obtained in the classical case, but the objects we are working here are slightly different. For example, this adjoint bundle also has this quotient. So now to conclude, I will show you, or I will present the present work we are doing and the future lines we would like to explore in order to somehow close the theory. First, we are working on generalizing these equations for more general Lie subgroups, because up to now we have only worked with this kind of subgroups, which are pretty easy to work with because the derivatives and the group are somehow separated. However, for more general Lie subgroups, the situation is harder. We have done a lot of work in this sense, but we have to conclude some details before we can show you the results. Then we would like to study the problem of reconstruction. What is the problem of reconstruction? When we have a section on the original bundle satisfying the Euler-Lagrange equations, we know that by means of reduction, we obtain a section on the reduced space satisfying the reduced equations. That's the philosophy of reduction. However, we can ask this question the other way around. If we have a section satisfying the reduced equations, can we ensure that is a reduced section from an original section satisfying the Euler-Lagrange equations? We know that the answer for this problem is no in general, but we need to pose additional conditions in order for that to be true. So we would like to know what are these conditions for the case of local symmetries. And at last, we would like to find applications of the theory. For example, we would like to apply it to gauge theories, and in particular to Young-Mills theory, which is the one used in the standard model of particle physics. In Young-Mills theory, the configuration bundle is the bundle of connections of a fixed principal bundle with group structure this calligraphic G. We know that Young-Mills theory, as any gauge theory, is gauge invariant, as the name states. But gauge transformations on a principal connection can be put in a bijective correspondence with sections of this Lie group bundle, the first jet of AD of P, being AD of P this associated bundle. So this allows us to define a fiber action on this Lie group bundle on our configuration bundle, which locally is given basically by gauge transformation of connections, like this expression. So we would like to explore this theory, and we would like to obtain, of course, the results of Utiyama's theorem. In other words, that the corresponding reduced space is the bundle of curvature associated to this principal bundle. So this would be all for today. Indeed, these are the main references, which are basically the articles of classical reduction in mechanics, this one, and in field theory, this couple of articles. And now, if you have any question or you would like to talk more deeply, we have the parallel session. So thank you.